A small comet C is passing near to a planet. The planet can be modelled as a sphere with centre O taken as a fixed point in space, so the motion of the comet is relative to the origin O. So you can see I've got my spherical planet here that's got a centre O. At the moment I've said that my comet is travelling in a straight line there. We were told that the diameter of the planet is 13,000 kilometres. The comet is modelled by satellites orbiting the planet. When the monitoring begins, the comet is at position vector there and is moving with vector there every hour, where the units are in thousands of kilometres. So the fact that we've got a diameter of 13,000 kilometres, remember the units are in thousands of kilometres, so in this model the diameter of the planet is 13. That's why I've marked on the radius of my planet as 6.5. I have written down the vector equation of the comet as if it was moving in a straight line, where that's its original position, given here. And we're told that it travels with this vector every hour, where lambda is the number of hours that have passed. So, part A, determine whether or not the comet will collide with the planet. So, the comet is going to be closest to the planet at this point here, and I need to see, is this distance here bigger than 6.5 or less than 6.5? If it's bigger than 6.5, then no problem at all. It's going to pass by the planet. But if that distance is less than 6.5, then it's going to collide with the planet. That's what we need to determine. So to do that, I've marked its general point on its trajectory as the 146 minus 21 lambda, 234 minus 33 lambda, and minus 85 plus 13 lambda. That's the general point of the comet along its straight line trajectory. And here, this is me working out the position vector from O to that point. So just doing this point, take away O, which is what I've done there. So that's telling me this vector from O to C. Now, at its shortest distance, I know that that's going to be perpendicular to the direction that the comet is travelling in. So I've done the dot product of OC with the direction that the comet is travelling in. Multiplying that out, so the 146 minus 21 lambda times minus 21 is this. This times this is this. This times this is this. Which then that gives me the equation to help me to work out that lambda is 7. So 7 hours have passed when the comet is closest to the planet. So I've then plugged that 7 into my vector OC, into this here. So I've put 7 here, here and here, as you can see here. And that's told me the position vector, the vector OC from the centre of the planet to the comet after 7 hours is minus 137. I've worked out its magnitude using some Pythagoras and found out that it is 6.782, not actually kilometres, because remember it's in thousands of kilometres, so that would be 6,782 kilometres away from the centre of the planet. That's bigger than the 6.5, it's bigger than the 6,500 kilometres, so therefore the comet will just about miss the planet. That is part A of this question done. Part B. We're told that the two satellites A and B have got position vectors. OA is 5i plus 12k and OB is 4i plus 12j minus 3k at the beginning of the monitoring, and they return to these positions every 4 hours. So I've just redrawn my diagram down here. Here's the planet. Here's the centre of the planet O. Here's one of the satellites A. Its position vector from the origin is the 5012 that we were told. Here's satellite B. Its position vector from the origin is the 412 minus 3 that we were told. And then I've got the comet travelling over here. The comet is currently here. We need to work out the expected angle ACB between the comet and the satellites A and B when they first return to their initial positions, which is after 4 hours. We were told that the satellites return to their positions every 4 hours, so when they first return to their initial positions will be 4 hours after the beginning. So I've used that 4 hours in my equation for the satellite to work out the position of the comet after 4 hours. So I've just said that lambda is 4, so I've done 146 plus 4 times minus 21, which gave 62. I've done the 234 plus 4 times minus 33, which gives 102. And then I've done the minus 85 plus 4 times 13, which gave the minus 33. So that is the position of the comet after 4 hours. And we want to work out the angle ACB. Well, I can work out the vector C to A by doing A take away C. Which gives minus 57 minus 102, 45. And I can do the similar thing for CB. So B, the 4, 12 minus 3, take away C. Which gives minus 58, minus 90, and 30. And now if I do the dot product, that's going to tell me the angle between those two vectors. That's going to tell me the angle ACB. So, cos theta is going to be the dot product of minus 57 minus 102, 45, with minus 58 minus 90, 30. And then we're going to divide by the magnitude of those vectors. And working all of that out, and then doing cos inverse of the answer. That gives me the angle between them as being 6.4 degrees. So that's the angle ACB 4 hours after they've started, so when they first return to their initial positions. And that's part B of this question done. Final part, part C, give a reason why the answer to part B may differ from the true value. Well, we could say that the comet is unlikely to travel in a straight line. For example, as it gets closer to the planet, you'd expect gravity to affect it more. and pull it towards the planet, so you'd expect it not to actually travel in a straight line. But any reasonable answer for why a limitation of our model here is a perfectly good answer for part C. Most of them you can say about not following a straight line, or the planet not being perfectly symmetrical, perfectly spherical, something along those lines.